Apache Hive. Hive provides a SQL-like interface for users to extract data from the Hadoop system. Since SQL knowledge is popular in the programming world, anyone familiar with it can use Hive. Broadly, the diagram shows how a SQL query is processed on the Hadoop cluster and can be stored or fetched from the storage components, either HDFS or HBase via a select from statement. Let's look at some of the features of Hive. Hive was originally developed by Facebook around 2007 and is currently an open source Apache project. Hive provides higher levels of abstraction by translating queries to MapReduce jobs, whereas Hadoop MapReduce provides lower level of abstraction via Java programming. Hive uses Hive QL and generates MapReduce or Spark jobs that will run on the Hadoop cluster. Hive is suitable for structured data, such as periodic reviews and analysis on historic data. Let's take a look at a case study of a leading online education company. This company uses Hive and Impala to analyze social media coverage. The organization analyzes positive, negative, and neutral reviews using Hive. Hive architecture. There are four main components as part of the Hive architecture. Hadoop core components such as HDFS and MapReduce, along with Metastore, drivers, and Hive clients. The Hadoop core components include HDFS. When data is loaded into a Hive table, Hive internally stores the data in an HDFS path, which is the default Hive warehouse directory. MapReduce. When a query is run, a corresponding MapReduce job is executed by converting or compiling the query into a Java class file. We then build a jar file and then execute this jar file. 2. A Metastore. The Metastore is a namespace for tables. It stores all of the metadata information related to the Hive, such as details related to the table, columns, partitions, and location on storage. 3. Drivers. Queries of the user after the interface are received by the driver are within the Hive. A concept of session handles is implemented by the driver. Execution and fetching of APIs modeled on JDBC/ODBC interfaces is provided by the user. And 4. Hive clients. This is the interface through which Hive queries are submitted. Hive CLI and beeline are some of the terminal interfaces, and web interfaces also include Hue and Ambari. Job execution flow in Hive. Let's list the steps involved in executing a query on Hive. First, Hive receives a SQL query and then performs the following steps to get the result. First, it parses the Hive SQL. It then makes performance optimizations and then plans the execution of the SQL query. It then takes this and submits the job to the Hadoop cluster. It then monitors the progress and then processes the data. The job is sent to the data processing engine, where it is either converted to MapReduce or processed by Spark. And finally, the data is stored in HDFS. Interfaces to run Hive queries. Hive offers many interfaces to run queries. The screen displays the Hive query editor. The command line shell for Hive is called beeline. Similarly, in Hue Web UI, you can access Hive through the Hive query editor. You can also connect Metastore Manager through the Open Database Connectivity / Java Database Connectivity driver, popularly known as ODBC/JDBC. In the next few screens, you'll view the screenshots and the demonstration to understand how to run queries using various interfaces. Connecting with Hive. Hive can be run using the beeline command line. The command line you see here is executed by typing in beeline. It will then return the version and the beeline prompt. Hue, which is an open source web interface for Hadoop, can be used to write a Hive query from an easy-to-use user interface, also known as a UI. You can click on the Hive or Impala option from the query editor to start writing a query in the respective tools. Running Hive queries using the command line beeline. The exclamation point is used to execute beeline commands. Here are a few commands that you can use to run beeline. First, to exit, use the exclamation point exit. This will exit the shell. Exclamation point help to show a list of all commands. And exclamation point verbose to show added details of queries. Running beeline from the command line. Below are several examples that you can use to execute a beeline command directly or using an HQL script. You can execute the file using the -u option by using the following command. Beeline -u -f for the file you'll pass to it, in this case Simplilearn.hql. You can use Hive QL directly from the command line using the -e option, using the following command. Beeline -u -e, and then in quotes select asterisk from users. Here, the space asterisk space from space users is the actual SQL query being executed. You can also use the command line shown to continue running the script even after an error. Beeline -u -force equals true, which is beeline space -u, connection string -hyphen force equal to true. Running Hive queries. You can execute any Hive SQL query from the Hive terminal or from beeline. A SQL command is always terminated with a semicolon as shown in the example. Hive editors in Hue. In the first diagram, there's a SQL query to create a SQL table named Simplilearn using the Hive editor. You can also view the Simplilearn table by writing Show Tables on the Hive editor. Once you click the Execute tab, it will automatically show the Simplilearn table on the Result tab. In Diagram 2, you can view the details of the Simplilearn table by typing Describe Simplilearn in the Hive query editor. The Hive Metastore. Managing data with Hive. Hive uses a Metastore service to store metadata for Hive tables. A table is simply an HDFS directory containing 0 or more files. The default path for the HDFS directory is /user /hive /warehouse/ and then table name. The table supports many formats for data storage and retrieval. The Metastore stores the created metadata. This is contained in an RDBMS such as MySQL. Hive tables are stored in HDFS and the relevant metadata is stored in the Metastore. So what is the Hive Metastore? The Metastore is a Hive component that stores a system catalog which contains metadata about the Hive tables, including things such as columns and partition definitions. Usually metadata is stored in the traditional RDBMS format. However, by default, Apache Hive uses the Derby database to store metadata. Any Java database connectivity or JDBC compliant databases like MySQL can be used to create a Metastore. There are a number of primary attributes that must be configured for a Hive Metastore. Some of them include the URL connection, the driver connection, the user ID connection, and the password connection. Use of Metastore in Hive. Hive uses the Metastore to get table structure and the data's location. As shown in the diagram, first the query is sent to the Hive server. Then the query reaches the Metastore to get the table structure and data location. Once the query receives the required information, the server queries the actual data on the table presented in the HDFS file system. The data warehouse directory structure. Now that we have looked at the use of Metastore in Hive, we will continue to look at how and where the data is stored. The given example /user/hive/warehouse is the default, and each table is a directory within the default location that contains one or more files. As shown in the diagram, we can visualize the Hive customer table stored in the following way. The Hive customer table stores data within the HDFS default directory, creating a new directory named Customers. Note that in HDFS, Hive data can be split into more than one file. In this case, we see the incoming data is split into file 01 and file 02. Hive Ddl and Dml. Let's understand how to define databases and tables. Databases and tables are created and managed using the Data Definition Language, or DDL, of HiveQL. These are very similar to standard SQL DDL statements. For example, you can use DDL to create, drop, alter, or specify the use of a database. Create a database. To create a new database, we will need to write the statement create space database space and the database name. In this example, we are creating a Simplilearn database. This will add database definitions to the Metastore, and it also creates a storage directory in the HDFS in the default location. To avoid an error in the case the database already exists, you will need to write create space database space if space not space exist space and then the database name. This will test to ensure that the database does not already exist prior to its creation. We'll now learn how to delete a database. Removing a database is very similar to creating a database. You need to replace the create command with the drop command. Drop space database name followed by a semicolon. In case the database already exists, you can type drop space database space if exists and then the database name semicolon. To remove a database if it has tables already, append the word cascade in the query. It will forcibly remove the database. Note, this might remove data HDFS file system as well. Now let's understand the process of creating a new table. The syntax to create a new table is the following. Create space table name, open bracket, the column name being defined, space, data type, close and bracket. Then define the row with row space format space delimited. Then the fields are fields space terminated space by space and the character that terminates a field. Lastly, stored as space open flower bracket text file space or space sequence file space or close flower bracket to indicate how the data should be stored. This syntax creates a subdirectory in the database's warehouse directory in HDFS. For the default database, the table will be stored in the default HDFS location. For the named database, the syntax will create a directory of dataname.db name inside of the default HDFS location and save the table in that directory. Now let's understand the syntax of create table in detail. The first line of the code is create space table name, open bracket column names, space data types, close bracket. Specify a name for the table and a list of column names and their associated data types. The second line of the code is the row space format space delimited, which states that fields in each file in the tables directory are delimited by some character. The default delimiter is Control A, but you may specify an alternate delimiter. The third line of the code is the fields space terminated space by space character, which specifies that each field of data is terminated. For example, tab delimited data would require you to specify fields that are terminated by /t. With the last line of code, store as space flower bracket text file space or space sequence file close flower bracket, you may declare the file format to be stored as a text file, which is the default and does not need to be specified. Let's see an example of how to create a table named Simplilearn. Data will be stored as text with 4 comma-separated fields per line. In this example, we specify create table Simplilearn, give it an ID of integer, a class of string, fees of integer, and then posted timestamp. So there are now 2 fields. Then we specify the row format as being delimited, and the fields will be terminated by the comma character. Data types. There are 3 data types in Hive. They're primitive, complex, and user-defined. Let's discuss each data type. Primitive types include integers, such as tiny int, small int, and big int. They also include Boolean, floating point number type, such as float and double, and string. Complex types include structs, maps, and arrays. And user-defined types include structures with attributes of any type. Let's look at how we can do these steps to change the table data location. By default, table data is stored in the default warehouse location, user /hive/warehouse. Use location to specify the directory where you want to put your data within HDFS. In this example, we are creating the Simplilearn table, and by using location, you can see we are specifying where the Simplilearn data will reside. In this case, it is /bda/Simplilearn. By default, tables are either internal or managed, in which data also gets deleted when the table is removed from the internal location. You need to use external to create externally managed tables. When you drop an external table, it removes only the metadata and not the data. Validation of data. Data in Hive are applied to a plan or a schema as is pulled out of a stored location, rather than pulling out the data directly. Therefore, Hive is a schema on read. Unlike RDBMS, they do not validate data on an insert operation. The files are simply moved into place, and loading data into tables is therefore very fast. Errors in file format will be discovered when the queries are actually performed and not during the load. Note, missing data will be represented internally as a null. Loading of data. Data can be loaded in the Hive table in the following 2 ways. First, directly move the data from the HDFS file to the Hive table using the HDFS DFS-MV syntax as shown in this example. Alternatively, load data by following the Hive syntax load space data space inpath /Simplilearn/data. Overwrite space into space table space Simplilearn. The overwrite keyword is optional, and it deletes all records before importing it. The overwrite keyword removes all files within the table's directory, and then moves the new files into the directory. Loading data from RDBMS. Scoop has a built-in support to import data into Hive and Impala. Using the Hive import option in Scoop, you can create a table in the Hive Metastore and also import data from the RDBMS to the table's directory in HDFS. Note, the Hive import option creates a table accessible in both Hive and Impala. What is hcatalog and what are its uses? Well, hcatalog is a Hive subproject that provides accesses to the Metastore. Uses of hcatalog are the following. It allows users to define tables using HiveQL's DDL syntax. It is accessible via command line and also via a REST API. It allows users to access tables created through the hcatalog from Hive, Impala, MapReduce, Pig, and so on. The file format types that are supported, the 4 different types are text files, sequence files, Avro data files, and Parquet format. Let's go over each of these file formats in more detail. The file format text file format is the most basic and a human readable file. It can be read or written in any programming language and is mostly delimited by commas or tabs. The text file format consumes more space when numeric values need to be stored as a string. It is also difficult to represent binary data such as an image. So, which format can be used to store an image in the binary format? Sequence file format, and the file format sequence file format can store an image in a binary format. They store key value pairs in a binary container format and are more efficient than a text file. The drawback is that a sequence file is not human readable. The file format Avro file format. This has an efficient storage due to the optimized binary encoding that it uses. It is widely supported both inside and outside the Hadoop ecosystem. The Avro format is ideal for long-term storage of important data. It can read from and write from many languages such as Java, Scala, and so on. The schema metadata can be embedded in the file to ensure that it will always be readable. Schema evolution can accommodate changes to the file. The Avro file format is considered the best choice for general purpose storage in Hadoop. File format Parquet. Parquet is a calmer format developed by both Cloudera and Twitter. It is supported in Spark, MapReduce, Hive, Pig, Impala, Crunch, and so on. Like Avro, schema metadata is embedded within the file. The Parquet file format uses advanced optimizations that are described in Google's Dremel paper. These optimizations reduce the storage space and increase performance. This Parquet file format is considered the most efficient for adding multiple records at a time. Data serialization. Data serialization. Before we start learning about the Avro format, let's understand about data serialization. Data serialization is a way to represent data in memory as a series of bytes. It allows you to save data to disk or send it across the network. For example, how do you serialize the number 1, 2, 3, 4, 5, 6, 7, 8, 9? Well, it can be serialized as 4 bytes when stored as a Java int and 9 bytes when stored as a Java string. A data serialization framework. Avro is an efficient data serialization framework, which is widely supported throughout Hadoop and its ecosystem. It also supports remote procedure calls, or RPC, and offers compatibility with programming environments without compromising performance. Let's take a look at the data types supported by Apache Avro and Avro schemas. The supported data types in Avro. We'll start with null. Null is simply an absence of a value. Boolean refers to a binary value. Int refers to a 32-bit signed integer, while long is a 64-bit signed integer. Float is a single precision floating point value. Double is a double precision floating point value. Bytes is a sequence of 8-bit unsigned bytes. String is a sequence of Unicode characters. Now that we've looked at the data types, let's also look at the complex data types that are supported in Avro schemas. First, record is a user-defined type composed of one or more named fields. Enum is a specified set of values. An array contains 0 or more values of the same type. Map is a set of key value pairs, where a key is a string, while value is of a specified type. Union is exactly one value matching a specified set of types. And fixed refers to a fixed number of 8-bit unsigned bytes. Hive Table and Avro schemas. Shown is an example that shows the equivalent of a Hive table within an Avro schema. You can see that when we execute the command create table orders and specified an ID field, a name field, and a title field with an int and 2 strings, the resultant Avro schema has the same information along with the metadata embedded within it. It begins with a namespace definition, which in this case is com.Simplilearn. Then the type, in this case a record, and then the name, which is called orders. The 3 fields are specified in the next section where we see name, ID, and then the type int. Then name, and the type string. Name, title, and type string. So the Avro schema contains all the same information along with the information for the record and the namespace. Avro also supports setting a default value in a schema as shown in the example. In this case, the name field has a default value of Simplilearn, and the title has a default value of Big Data. Creating a new table with Parquet. You can create a new table in Hive and store it in the Parquet format. In this example, a new table and a new order is being created to access existing Parquet format data. It begins by activating impala-shell at the command line. Then we execute the create external table new order like Parquet and give it the field that's going to be used to define how we store it, Simplilearn order.parquet. Then we say store this as a Parquet formatted data set, and then we specify the location Simplilearn/new_order. Parquet files are in binary format and therefore cannot be read easily. To read Parquet files, you can use a tool called Parquet-tools as shown on the screen. Activating Parquet-tools passes the head command along with the file you wish to read, in this case orders.parquet. At that point, it will dump the Parquet file out to your terminal. Hive Optimization, Partitioning, Bucketing, and Sampling. Data storage. In the previous lessons, you have learned that by default, all files in a dataset are stored in a single Hadoop distributed file system, or HDFS directory. Hive is considered a tool of choice for performing queries on large datasets, especially those that require full table scans. Hive has advanced partitioning features. Data file partitioning is very useful to pruning data during a query in order to reduce query times. There are many instances where users need to filter the data on specific column values. Using the partitioning feature of Hive that subdivides the data, Hive users can identify the columns, which can be used to organize the data. Using partitioning, the analysis can be done only on the relevant subset of data, resulting in a highly improved performance of Hive queries. In case of partitioned tables, subdirectories are created under the table's data directory for each unique value of a partitioned column. You will learn more about the partitioning features in subsequent sections. Example of a non-partitioned table. In non-partitioned tables by default, all queries have to scan all files in the directory. This means that Hive will need to read all of the files in a table's data directory. This can be a very slow and expensive process, especially when the tables are large. In this example, you can see that there is a state column created in Hive. The requirement is to convert this to a state-wise partition so that separate tables are created for separate states. The customer details are required to be partitioned by state for fast retrieval of subset data pertaining to the customer category. Here is an example of a partitioned table. This example shows you how the previously non-partitioned table is now partitioned. You can see that the state column is no longer included in the create table definition, but it is included in the partition definition. Partitions are actually horizontal slices of data that allow larger sets of data to be separated in a more manageable chunk. This essentially means that you can use partitioning to store data in separate files by state, in this case, as shown in the example. At the time of table creation, partitions are defined using the partitioned by clause with a list of column definitions for partitioning. A partition column is a virtual column where data is not actually stored in the file. In this case, if you had all 50 states represented in your data, you would have 50 separate partitions, each of which could be queried independently and directly. Data insertion into a partition table can be done in two ways or modes. The first is static partitioning. The second is dynamic partitioning. We'll learn more about these concepts in subsequent sections. First, let's begin with static partitioning. In the static partitioning mode, you can insert or input the data files individually into a partition table. You can create new partitions as needed and define the new partitions with the Add Partition clause. While loading data, you need to specify which partition to store the data in. This means that with each load, you need to specify the partition column's value. You can add a partition in the table and move the data file into the partition of the table. As you can see in this example, you can add a partition for each new day of account data. So for a year's worth of data, you would end up with 365 different partitions, all manually created. Now let's look at dynamic partitioning. With dynamic partitioning, partitions get created automatically at load times. New partitions can be created dynamically from existing data. The partitions are automatically created based on the value of the last column. If the partition does not already exist, it will be created. In case the partition does exist, it will be overwritten by the overwrite keyword as shown in the example. As you can see, a partition is being overwritten. When you have a large amount of data stored in a table, then using a dynamic partition is suitable. This example basically refreshes the state data with the customer ID, first name, last name, address, and so on, each time the command insert is executed, since we have added the overwrite clause. Dynamic partitioning in Hive. Keep in mind that by default, dynamic partitioning is disabled in Hive to prevent accidental partition creation. To use dynamic partitioning, you need to enable it by using these settings. Here we see set hive.exec.dynamic.partition equals true. Then we say set hive.exec.dynamic.partition.mode equals non-strict. This allows us to use dynamic partitions. Now that you've learned about the two modes of data insertion into partition tables, let's take a look at some of the commands that are used to support Hive partition tables, which lets you view and delete partitions. You can view the partitions of a partition table by simply using the show command. So in this case, access Hive and then show partitions, in this case, accounts. Delete the partition. To delete the partitions, you simply can drop them using the alter command as shown in the image. By using the alter command, you can also add or even change partitions. When to use partitioning. Following are the instances when you need to use partitioning for tables. First, if your reads and queries are taking too long, reading the entire dataset may indicate you want to use some partitions. Also, queries will almost always filter on the partition columns. If you have a large number of queries that are filtering a specific column, you may want to add a partition for that column. And last, there are a reasonable number of different values for partition columns. If you're going to use partitioning, you typically don't want just 2 values. You may want several to increase the performance of your queries. So when is not a reason to use partitioning? Well, here are some instances when you should avoid using a partition. 1, avoid partitioning on columns that have too many unique rows. You'll end up with way too many partitions. Also, be cautious while creating dynamic partitions, as it can lead to a very high number of partitions if, for example, you create a new partition for every zip code in the US. Also, try to limit partitions to less than 20K in size. Bucketing in Hive. You've seen that partitioning gives results by segregating Hive table data into multiple files only when there are a limited number of partitions. However, there may be instances where partitioning the tables results in a large number of partitions. So what can be done in situations where over-partitioning can become a problem? This is where the concept of bucketing comes in. Bucketing is an optimization technique similar to partitioning. You can use bucketing if you need to run queries on columns that have huge data, which makes it difficult to create partitions. In the example shown, you can see that we have country, along with a column that's being used to create partitions, in this case, state. So we'll end up with 50 states in the US for the partitioned column. Within the state, there are many, many cities. So in order to optimize these queries, we can implement bucketing, which would take all the cities that have the same hash code and place it into the same bucket within the cluster of buckets. This will allow you to specify how many buckets you wish, 10 buckets or 100 buckets. The larger number of buckets, the shorter the fields that will be used to put cities in. If you have a large number of buckets, therefore, you'll have a very flat set of data within each bucket. If you only have 5 buckets, then you'll have many more records within that bucket that will be using the feature of a bucket. So what do buckets do then? Well, based on the previous example, we saw that they will distribute the data load into user-defined sets of clusters by calculating the hash code of the key mentioned in the query. For example, a city would create the same hash code each time a hash code is needed. So here's a syntax for creating a bucket table. As per the syntax, the data would be classified depending on the hash number of user_ID into 100 buckets. The processor will first calculate the hash number of the user_ID in the query and will then look for only that bucket. This will tremendously speed up the ability to find the data by calculating a hash and then getting the record out of the bucket. Hive Query Language Introduction. Hive is a SQL-like query language for Hive to process and analyze structured data in a metastore. A simple example uses a select statement looking for the field DT, counting the number of distinct uses of user ID from events table, and then grouping by DT, date. HiveQL, Extensibility. An important principle of HiveQL is extensibility. HiveQL can be extended in multiple ways. One is pluggable user-defined functions. Two is pluggable MapReduce scripts. Three is pluggable user-defined types. And last is pluggable data formats. You'll be learning more about user-defined functions and MapReduce scripts in subsequent lessons. Hive Analytics, UDF and UDAF. UDF is a user-defined function. Hive has the ability to define a function. User-defined functions, or UDFs, provide a way of extending the functionality of Hive with a function which is written in Java that can be evaluated in HiveQL statements. All user-defined functions extend the Hive UDF class. After that, a UDF subclass then needs to implement one or more methods named evaluate, which will be called automatically by Hive. Evaluate should therefore never be a void method. However, it can return a null if required. Code for extending UDF. Here is some code that you can use to extend the user-defined function. Here you can see we've included the package com.example.hive.udf. And we've done two imports, one on org.apache.hadoop.hive.ql.exec.udf, and also org.apache.hadoop.io.text. This allows us to declare a function public final class lower, which will extend the UDF, and the command public text evaluate final text s, where if s is equivalent to null, then return null. Otherwise, return new text and then execute the text to string to lowercase function. This will allow us to read the text in and convert it to lowercase using our own custom-defined UDF. Built-in functions of Hive. You've learned that writing the functions in JavaScript creates its own UDF. Hive also provides some built-in functions that can be used to avoid creating your UDF from being created. Let's take a look at what these built-in functions are. These would include several categories, including mathematical, collections, type conversions, date, conditionals, and strings. Let's take a look at the examples provided for each of the built-in functions. For mathematical operations, you can use the examples of round, or floor, or random, or ceil. For collections, you can use size, map, and arrays. For data type conversions, you can do things such as cast. For dates, you can use the following APIs, such as from Unix time to date, years in datediff. For conditional functions, you can use if, case, and coalesce. And for string files, you can use things such as use length, reverse, upper, and trim. Let's take a look at some of the other functions in Hive, such as the aggregate function and the table generating function. Aggregate functions create the output if the full set of data is given. The implementation of these functions is very complex compared with that of the UDF. The user should implement a few more methods, however. The format is similar to UDF. Therefore, Hive provides many built-in user-defined aggregate functions, or UDAF. Normal user-defined functions, such as concatenate, take in a single input row and give out a single output row. In contrast, table generating functions transform a single input row to multiple output rows. Shown here is a lateral view that is used in conjunction with table generating functions. A SQL script in lateral view is displayed on the screen. Consider the base table named page ads. It contains two columns, page ID, which is the name of the page, and ADID _list, which is an array of ads that appear on the page. A lateral view with the explode can be used to convert the addid_list into separate rows using the provided query. MapReduce scripts. Let's take a look at the MapReduce scripts that help extend the HiveQL. MapReduce scripts are written in scripting languages such as Python. Users can plug in their own custom mappers and custom reducers into the data stream. To run a custom mapper script or a custom reducer script, the user can issue a command that uses the transform clause to embed the mapper or the reducer script. Look at the script shown on the screen. Here, the key value pairs will be transformed to string and then delimited by tab before feeding to the user script by default. The method strip returns a copy of all the words in which whitespace characters have been stripped from the beginning and the end of the word. The method split returns a list of all the words using tab as the separator. Now that you've learned about udf/udaf and MapReduce scripts, let's compare the user-defined and user-defined aggregate functions with MapReduce scripts. The table here shows the comparison. User-defined functions are written in Java, while MapReduce scripts can be written in any language. Both user-defined functions and MapReduce scripts support one-to-one, n-to-one, and one-to-n input to output. However, user-defined functions are much faster compared to MapReduce scripts, since the latter spawns new processes for different operations.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.